So, good morning all of you. Let us look at the flux quantization, which is a very important concept in the context of superconductivity today. And in order to understand flux quantization, we will have to go back to the London equations, the equations that we have learnt little bit in brief on this effects of electromagnetic fields in superconductors. So, let us start with London equations and then we will go over to the flux quantization. So, to start with London equations, so what is the condition for the transport of charges even if they are interacting amongst each other. So, if the charges are interacting amongst each other, they should create resistance or they should give rise to resistance. So, how is that we are encountering a situation in which the current is flowing without any resistance, which means that the electrons would stop interacting with each other? We of course know partly the answer to this question, but here what London and brothers, London brothers actually they have suggested is that whenever there is a slowing down or there is a resistance that arises due to the interaction of electrons among the electrons, then there is a external electric field that would overcome this effect of the interaction and would eventually give rise to a resistance-less motion. So, in order to see that, let us write down Newton's laws for a charged particle in an electromagnetic or rather in an electric field here. So, we write it with m star which is the effective mass of the particles that are contributing to the motion, which we know that there are Cooper pairs, or we are going to see more elaborately the formation of Cooper pairs and so on. And then there is, so this is the Newton's laws which says that, so this is nothing but the Newton's laws. For a charged particle of charge E star, of course, you can relate that charge E star is nothing but equal to twice of the electronic charge, and this electronic charge is it's as you know that it's 2E or the Cooper pair, but that will come to later. Let us simply look at this equation and try to understand that what it does or what it gives. So, m star is the effective mass and E star is of course the effective charge. Okay. And now, the current density or the supercurrent density is written as Js is equal to Ns E star and Vs. This is all familiar to you. Js is the current density, Ns is the super electron density or the super fluid density as it is called. Basically, it is the density of super electrons, and Vs is the velocity of these super electrons, and of course, E star is just the electronic charge. So, that is the current density equation that one would get, and we can write it using a mod star here of Vs, and the minus sign is just to make sure that the current density is actually in a direction which is opposite to the direction of the flow of the super electrons. Okay. So, if you call this as equation 1 and call this as equation 2. So, if you put 2 into 1, one would get the first London equation, which is of the form that mu 0 lambda L square a djs dt is equal to E, where this lambda L is equal to m star divided by mu 0 n s E star square, and it is called as the penetration depth. And we know that physically what it means is that the depth or the distance till which the magnetic field can penetrate into the sample, or more precisely this is the distance over which the magnetic field actually penetrates and falls into a value of 1 over E of the value that it has at the surface. So, it is called as a penetration depth, and it is one of the most important length scales of a superconductor. And there is another length scale that we have looked at, which is called as the coherence length. And so, this is the equation that we get, and let us call this as equation maybe 3. And then of course, if I take the curl of both sides of equation 3, so taking curl of both sides in 3, we have mu 0 lambda L square and a del t of curl of J s, it is equal to curl of E, which is nothing but equal to minus of del B del t by Maxwell's equation. And now this requires minute of discussion here, that you see there was a djs dt, or we can simply write it as ddt of that instead of writing. So, this is a ddt. Now, you see that we need to take a curl is a space derivative, and because there is a time derivative, we can interchange the space and time derivative. So, we have interchanged that and have written the curl inside and which is taken directly on Js, and the ddt has come out. So, this call it as equation 4. Let us look at what happens to this the right hand side of the equation by using Maxwell's equation again. We can write down the curl of B. This is equal to a mu 0 epsilon 0 del E del t and plus a mu 0 j and if we use this, then we can write down this lambda L square del square of del B del t. This is equal to a del B del t, and this equation since it is true for the rate of change of magnetic field with time, it should also be true for the magnetic field itself, and we can write this down. So, this is a special case that we are considering, that where the rate of change of magnetic field is actually taken to be same as the magnetic field. So, we have ignored, or rather we have taken this the value of the magnetic field at the surface to be equal to 0, and in which case we can write down the same equation as for simply B, and that is written as so let us write it with this. So, it is a this is equal to B, and since B is equal to mu 0 J s, so this B actually looks like it is equal to minus mu 0 lambda L square curl of J s. Okay. So, this is the equation, this is one of the London's equations, where the magnetic field is expressed in terms of the current density or the curl of the current density. So, if we introduce the magnetic vector potential, which is defined by B equal to curl A, and then of course, the J s can be written as minus 1 by mu 0 lambda L square A, because of this of course, that your B is equal to curl A. So, that is the relation between the J s and A. So, this is basically called as the second London equation. And just to rectify that we have not written, this one was written as the first, this one is written as the first London equation. All right. So, these are the two London equations that we get, but what are they good for? What do they convey? And can we extract some more information out of them? That is the question. So, of course, we know that curl of E is equal to minus del B del T, and the curl of so E minus mu 0 lambda L square del J s del T, or you can write it as d J s dt as well. So, this is equal to 0. So, which means that if a curl of vector is equal to 0, that vector should be written, or rather one should be able to write that vector in terms of a gradient of a scalar quantity. So, E minus mu 0 lambda L square, we will call it d J s dt just to make matters simple. Let us change that as well here. And so, this is equal to nothing but a phi, where phi is a scalar. So, once that is done, one can easily understand that the grad phi dot J s, it's equal to 0, because of the reason, if I take a dot product with the current density, or the super current density, that should give me equal to 0. So, that tells that there is no component of grad phi in the direction of J s. Okay. And so, which means that the J s dotted with the electric field should be equal to 0, and which is basically a restatement of nothing but the first London equation. Okay. And this is basically, it looks very reasonable, for the reason that there is no the energy dissipation is 0 in a constant magnetic field, which should be correct, because otherwise it would have violated conservation of energy. So, this in a way it says that no energy dissipation in a constant magnetic field, that is because the magnetic force is is a Lorentz force which goes as V cross B, and the energy dissipation is called as the power, and the power goes as F dot V. So, if V cross B is dotted with V, then that has to be 0. This is a common wisdom, and this is basically saying the same thing. And it says that the conservation of energy is valid, or a very important thing at this moment. This is strictly true for what is called as a simply connected superconductor. Okay. So, let me write that in big and bold. If we have a multiply connected superconductor, I will just tell you what multiply connected superconductor means. In a multiply connected superconductor, there could be a component of E that is, if we dot it with the supercurrent density, it may not still give it equal to 0, which means that the grad phi perpendicular to Js may still be admissible for a multiply connected superconductor. So, let me write that once again. So, Js perpendicular to grad phi, which is nothing but the electric field, or say that not perpendicular to grad phi could still be admissible. In a multiply connected superconductor. So, this is one of the important statements that we make here, and in order to justify that and get a connection with flux quantization, we will define what a multiply connected superconductor is. So, if this superconducting specimen, so this is a superconductor everywhere. Okay. So, it is there is no hole, there is nothing. So, this is called as a simply connected superconductor. And there is a hole there. So, this region where I write hole is not superconducting. So, I put a thatched area to denote that it is superconducting. So, this area is superconducting, and the whole area is not. So, this is anything other than superconducting. So, this is called as a multiply connected superconductor. So, why did we introduce this in the first place? The reason that we introduced it is that we wanted to show flux quantization, that if there is a hole in a superconducting region and the superconductor is called as a multiply connected superconductor, put it in a magnetic field, the flux lines will thread or penetrate through this hole, and cannot take any value. It takes only values that are perpendicular, that are quantized in some known quantum, which is called as a flux quantum. Will tell you the value of that, and so there could be one flux quantum, or there could be two flux quantum, or there could be three flux quantum, but nothing in between. There's no half or 1.5 flux quantum and so on. So that's one. The other thing is that what in line with the preceding discussion, we have said that the grad phi dot Js is equal to 0, or rather the E dot Js is equal to 0. So basically there is no energy dissipation, and E and Js are always perpendicular to each other, and that is why the dot product vanishes. Because you know the dot product comes with of two vectors, that comes with a cos theta. Theta is the angle between the two vectors, and if theta is equal to 90 degree, then of course the angle goes to so the cos of that angle that becomes 0, and so the whole quantity vanishes. So here we want to show that also in a multiply connected superconductor, the E and Js, they do not have to be necessarily perpendicular. Now, in order to show both of these, let us look at basically we will just we have looked at enough quantum model of superconductivity, and going to see enough of that in the future. But however, just to formally once again write it, so we will say quantum model of superconductivity. And very interestingly, this has relevance with the fact that the quantum mechanics is usually seen in microscopic and submicroscopic scales, or rather very small length scales, and inside an atom, and maybe inside a nucleus and so on. However, superconductivity is one such example in which quantum phenomena or quantum mechanics manifests itself in macroscopic scales. Okay. So, we can have a big superconductor which could be extending over many sort of coherence length or penetration depth, and still the quantum formalism or the formulation of quantum formulation of superconductivity still holds, and we can write down a wave function corresponding to that quantum regime, and let us call that wave function as psi of x t, where it is written as an amplitude and a phase, where theta is called as a phase. So, theta psi is the amplitude, and theta is actually called as a phase, and it is a real quantity. Okay. But what is the physical significance of that? The mod psi square is the super current density or the super electron density, as we know. So, in a homogeneous superconductor, Ns is does not depend upon the space variable, and in an inhomogeneous superconductor it can depend upon the space variable or space coordinates. So, let us write down the canonical momentum for a particle of charge E star and mass m star. So, that is given by P equal to m star V s plus a E star A. So, this is the in an electromagnetic field where A is the vector potential. Of course, we can choose a gauge in which phi equal to 0, and also the divergence of A equal to 0. So, this can be written as a minus I h cross del psi by writing P as so this can be in a way this can be operated on psi and this m star V s plus E star A psi and so on, and then you write P is equal to minus I h cross del. So, this becomes equal to minus I h cross del psi, which is equal to m star V s plus a E star A psi, and so on. And now then of course, your psi is equal to, as written above, it is equal to psi to the power I theta. So, a del psi is nothing but equal to psi e to the power I theta del theta, and at this moment we are assuming that we are talking about a homogeneous superconductor, and in which psi is this amplitude is independent of position, and it is only the phase that depends on the special coordinates. So, if you put it here, then it becomes equal to a minus I h cross, and there is a I delta theta and a psi. This is of course equal to a m star V s plus a E star A psi. If you do a simplification, then that becomes equal to, because your minus I into I will become equal to 1 h delta theta. So, this is equal to a m star V s plus a E star A, and this is psi. Well, I mean I have taken off psi from both the sides, and this can still be written as a h cross by E star delta theta. This is equal to a mu 0 lambda L square J s plus A. That is because the J s is equal to N s E star V s. That is the equation for, or the defining equation for the current density. So, the J s divided by N s E star into m star is equal to m star V s, and then I can introduce this lambda L, which was defined earlier by this equation, by this lambda L square is equal to m star divided by mu 0 n s E square or E star square, and that is going to give me this. And so, this is basically, so we can write down so this is an equation that is coming from the London equations, and that is why all this exercise of explaining this London equation is being done. Let us see what it takes us from there. So, I can write down the J s, it is equal to E star h divided by m star n s, and there is a del theta and plus a 2 E star by h cross and A, sorry, the A has to be in the numerator, A, and so on. I believe this is h cross, one can check that. So, this is the expression for this, the current density or the super current density. Just to remind you that, let me also write down the lambda L square is equal to m star mu 0 n s E star square. Okay. So, that is the equation that one gets, and so J s becomes equal to this, and where of course all these things are very familiar to you. Theta is the phase of the wave function. So, we are getting a gradient of the phase, and let us see that how this gives rise to the quantization. Let us take a multiply connected superconductor like this, okay, which has got, of course, this closes smoothly, do not so there is a hole there. Okay. So, this region is superconducting and this region is a hole. Let me take a path, I draw it by a dashed line, a path, okay, and this path, let me call this as L, And of course, because it is in the superconducting, it falls into the superconducting specimen, the Js should be equal to 0 here, because otherwise of course, so this Js should be equal to 0 along this line inside the superconducting sample, and that tells that so along a closed loop L. So, since we have taken a closed loop, the net superconducting current density along the closed loop would be equal to 0, which means the coefficient cannot be equal to 0. So, the term that is there on the right inside the bracket should be equal to 0, which says that delta theta plus a 2 E star over H cross A has to be equal to 0, which says that delta theta has to be a minus 2 E by H cross A, and that is equal to that. So, this is the variation of the phase and its relationship to the magnetic vector potential. So, if you integrate, let us call this as equation 1 here. So, if you integrate 1 over L, then one can get, so it is a closed integral. So, it is a gradient of theta dotted with dl. So, we take a small element of length along that capital L or that contour, the dashed contour is equal to dl, which is nothing but equal to minus 2 E by H cross, and this is equal to A dot dl. So, I can use Stokes theorem, which says that the line integral or the closed line integral of any vector can be written as the curl of the surface integral of the curl of the vector, which means this is equal to minus 2 E by H cross, and this is equal to a curl of A ds, where this S is basically the surface area of the, I mean where the contour is found by L, and S is the corresponding surface area. Now, since you know that curl of A equal to B, so this is equal to minus 2 E by H cross, and this is a B dot ds, and B dot ds is nothing but the magnetic flux. So, this is equal to a minus 2 E by H cross and a phi, which is called as a magnetic flux. Let us write it with a capital phi. So, now remember that our theta is actually the phase of the wave function. Now, we always demand that the wave function is a single valued quantity. Okay. Wave function cannot be multiple valued unless we make a full circle of the phase. Otherwise, it will lead to the ambiguity in the probability density if we do not enforce the single valuedness of psi. So, this is then equal to, if you enforce single valuedness of psi. So, this is equal to 2 pi n, it is equal to minus E by 2 H cross phi, that is coming from the top line. So, that tells that, so this means that 2 pi n equal to 2 E over H cross phi, it is equal to phi over phi 0, where of course, we have written that a n phi 0, it is equal to phi. So, the flux through the hole that you are seeing should be quantized in terms of a phi 0, certain phi 0, and it can only take values n equal to 1, n equal to 2, n equal to 3 and so on. N equal to 0 is a special case where we have a simply connected superconductor, and this of course gives that the phi 0 value is equal to 2 pi H cross over 2 E, which is equal to H over 2 E, and if you put the value of H and E, which comes out to be H is of course your the Planck's constant, which is 6.6 10 to the power minus 34 joule second. E is equal to 1.6 10 to the power minus 19 coulomb. All these things you will find in any of the data book that one comes across, and this is equal to a 2.0679 into 10 to the power minus 15 Tesla meter square. So, this clearly shows that the flux that can pass through the hole is quantized, and the quantum of flux, which is an important quantity, the quantum of flux is this value 2.0679 10 to the power minus 15 Tesla meter square. It has of course the magnetic field multiplied by the area, that dimension, and so these are experimentally observed, and this comprehensively shows that electronic the E star that takes part in this particular calculation is nothing but equal to 2E. So, which says that there are 2 electrons that are responsible and that are relevant for these the carrying of the supercurrent, and which we know are called as the either you call it them as super electrons, we know that they are called as the Cooper pair.